We're going to start a new section here, Systems of Linear Equations in 3 Variables, 11.2 in the textbook. Before I talk about 3 variables, I would like to review a bit. In previous math classes, we learned to solve a system of 2 linear equations in 2 variables. So here's an example. Solve the system x minus 3y equals 1, 3x minus 8y equals 2. So these equations are called linear because each has a graph that is a straight line in the xy plane. I think we're pretty familiar with graphing straight lines in the plane. A solution to the system consists of 2 numbers, a value for x and a value for y, that satisfy both equations. Now there are several methods for solving systems of equations. You probably have learned several of these. You could graph the 2 lines and find the coordinates of the point where the 2 lines cross. The one method I want to refer to here, though, is the substitution method, because that's the method that we're going to use, we're going to extend to 3 variables. So here, let's just go ahead and solve this system using the substitution method. I'm going to label these equations 1 and 2. So again, this should be something you're very familiar with. If I take equation 1, I could isolate a variable, and actually I could pick either equation. I'm going to pick equation 1 because it's pretty easy in equation 1 to isolate x in equation 1, that x minus 3y equals 1. If I add 3y to both sides, I get x equals 3y plus 1. And then I'm going to substitute into the other equation. So I want to say I isolate x in one equation. I pick the first equation, and then I'm going to substitute into the other equation. I'll take equation 2, 3x minus 8y equals 2. And I'm going to replace x with this expression 3y plus 1, right? So I have 3 times 3y plus 1 minus 8y equals 2. And we get an equation of one variable that we can now solve for y. 9y plus 3 minus 8y equals 2. Combine like terms, 9y minus 8y is y plus 3 equals 2. Y is going to equal negative 1. And then I have to find the corresponding x value, right? And I can plug in, I'm going to actually come up over here, x is equal to 3y plus 1. X is equal to 3 times negative 1 plus 1. Negative 3 plus 1 is negative 2. So my solution is x equals negative 2, y equals negative 1, a value for x and a value for y. Or sometimes we just write that solution as an ordered pair, negative 2, 1 in parentheses, right? That represents the coordinates, the point where the 2 lines cross. Now, in this problem, we found that there was exactly one solution. So this system has exactly one solution. I just want to remind you that sometimes there is no solution. Sometimes there are infinitely many solutions. And we're not going to go through all those different possibilities here. I'm just trying to remind you of stuff from earlier algebra classes. So, okay, that was just our little review of a system in two variables and two equations. So now what we're going to do, and this is something new, we're going to look at three equations and three variables. And a linear equation in three variables may be written in the form ax plus by plus cz. So there's a third term for this variable, cz. For the third variable, z equals d, where a, b, c, and d are numbers. And here's an example of a system in three variables. 2x minus 3y plus equals 10, x plus 5y plus 2z equals 3, x minus 2y minus z equals 1. So we have three separate equations. Each one of these equations is called a linear equation. Now, they have graphs too, but to graph an equation in three variables, you actually need three dimensions. You need an x, a y, and a z axis. The graphs of these equations are not actually lines, they're planes. They're two-dimensional planes, like flat sheets, sitting in three-dimensional space. So we still call them linear equations, though, even though their graphs are not lines. Their graphs are planes. And how do you recognize a linear equation? You know, the way to think of it, the algebra of all this is we have each variable occurring to the first power, and we have no variables being multiplied together. So in the symbols, that's how we recognize that these are linear equations. So what I want to do is just one exercise here where we're going to show that 2, negative 1, 3 is a solution to the system above. Now, I'm writing that solution as what's called an ordered triple of numbers, similar to an ordered pair, but now we have three values. The first number is always the x value, so x is equal to 2. The second number is the y value, y equals negative 1. The third number is the z equals 3. So you could write it either way. 2, negative 1, 3 is a nice compact way to write the solution. Or you could just write it out as x equals 2, y equals negative 1, z equals 3. So what we need to do is verify in each one of the three equations, right? We got 1, 2, 3 equations. Here I'm going to take my first equation and just recopy it. 2x minus 3y plus z equals 10. So to do our exercise here, where we want to show that 2, negative 1, 3 is a solution, I have to plug in. So I'm going to plug in 2 times 2 for x minus 3 times negative 1 for y plus 3. And I'm asking myself, is that equal to 10? 4 plus 3 plus 3, is that equal to 10? 10 equals 10. Checks out in equation 1. Now we got to do that for each one of these three equations. Equation number 2 is x plus 5y plus 2z equals 3. And so I plug in again, 2 for x, 2 plus 5 times negative 1 for y plus 2 times 3 for z. I'm asking myself, is that equal to 3 on the right-hand side? 2 minus 5 plus 6, is that equal to 3? 8 minus 5 is 3 equals 3. Checks out. And then I have one more equation to verify. Since I have 3 equations to begin with, I also have to check x minus 2y minus z equals 1, my third equation. Plugging in 2 minus 2 times negative 1 minus 3, is that equal to 1? 2 plus 2 minus 3, is that equal to 1? I get 4 minus 3 is 1 equals 1. Checks out. So we have done our exercise where we verified that 2, negative 1, 3 is a solution to that system. So now in the next video we'll actually solve a system of 3 variables and 3 equations.